You start the presentation.
The transmission online, yeah.
Transmission online.
Okay, so I will start.
Yes. No, 2 minutes because people is coming.
Okay.
1 or 2 minutes.
Yeah, and this is the first time that we are starting on Thursday, so
yes.
Yeah.
Maybe we should wait a few more minutes.
Yep.
And it's the first conference in the year, and everybody after vacation, like
And so now that everything is registered, we cannot say what we did for holidays, right?
Yes.
Okay, maybe we will start soon, right? What do you think?
Yes, we can start now. We want.
Yes, go ahead.
Yes.
Okay.
Enrique, do you want to introduce the speaker?
Okay,
Yes.
very well. Well, good morning, good evening, or good afternoon for everybody. And as you see, we are going to begin with this, let's say, third step in the web seminar. This year, we are going to, we have prepared the schedule on Thursday in order to avoid coincidence with that, other seminars, web seminars that are near to this one. And our first session will be, as usual, a double young session, double session for young speakers. And the first speaker is going to be Kuntal Bhandari, who is going to present joint work with Frank Boyer and Victor Hernandez Santamaria under the title Boundary Controllability of Some Coupled Parabolic Systems with Kirchhoff Conditions. So you can start, and thank you very much for accepting to participate in this web seminar, and it's you now.
Yes, thanks to you, and thanks for inviting me for this talk also. Thank you very much for the introduction, and thanks to everyone for being here in my presentation. As Enrique told, that my presentation will be about some boundary controllability of coupled parabolic systems with Kirchhoff type of conditions. And the main part of my talk will be a joint work with Frank Boyer and Victor Hernandez Santamaria. I start by giving some outline of my presentation. I will start by giving some introduction and motivation for my work, and in the second part I will talk about the main thing, which is concerning the boundary controllability of two closely coupled system. And in this case, there will be two subcases when the control is acting the second component, and in this case we will handle the controllability string by Carl-Lemon approach. And secondly, we will put the control on the first component, and in that case, Carl-Lemon trick will not work, and I will discuss, of course, why it's not working. And this case will be handled by moments approach. Finally, in the last section, I will talk about some three closely coupled system with only one control. Okay, so this is the outline, and then I will go to the motivation or introduction part. I start by considering a parabolic control system on a metric graph, mainly a star-shaped graph of n edges and n plus 1 nodes. Obviously, in the picture, there are only 7 edges, but one can think of n edges. So in each edge, we have a partial differential equation, parabolic PDEs of y1, y2 until yn. They are satisfying some kind of Kirchhoff condition on the red node, that is the center of the star-shaped graph, which is nothing but a mixture of continuity condition as well as a flux condition. On the outsider node, we're putting Dirichlet kind of boundary controls, n-1 boundary controls, where the number of edges are n. And the null controllability of this system can be written as follows. The system is null controllable for any initial data y0 from h-1 to the power n space, if and only if we are putting n-1 control. And this kind of control systems has already been appeared, for instance, in the book by Degas-Bourgeois and also the survey paper we are doing. Now, from motivating from this kind of problem, our main goal is to see what happens if we put some kind of interior coupling as well beside the boundary coupling. And this is the main system of our concern. There is the system 3 that consists of 2 cos 2 model with 1 interior coupling to the second equation through the first component y1. The interior coupling coefficient A is real number. Obviously, if we choose A is 0, that is, there is no interior coupling, then putting control on both components are giving the same result. But as soon as A is non-zero, putting control on both components will give different features, and we will discuss about this in the talk. Before going to the main results or main theorems, I will talk about some functional settings. So I start with the diffusion coefficient gamma I, which are continuously differentiable on closed interval 0, 1, such that they are satisfying some kind of coercivity condition. The functional settings are briefly written in this slide. I start by denoting A alpha, which is the vectorial diffusion operator, and the domain consists of all the elements U from H2, such that U1 equal to U2 is 0 at point 0, and they are satisfying Kirchhoff condition at point 1. The coupling matrix is denoted by AMA, and then the non-self-adjoint operator A alpha A, which is nothing but addition of the self-adjoint operator A alpha with the coupling matrix MA. Their domains are the same. We also denote the adjoint operator by A star alpha A with the same domain. And finally, we consider the space script H, which is nothing but the domain of A half, and this is as a completion of domain of A alpha with respect to the norm given by equation 5. QH is some quantity that I have written here. And indeed, one can show that this space H is nothing but it's consisting of all the elements from H1, such that they are satisfying the Dirichlet elements from the domain of A alpha. Finally, we denote the dual space of H by H-1 with respect to the pivot space L2, and the observation operators for the first and second cases are denoted by BI star, I is 1, 2, which is nothing but the co-normal derivative of the component U, component-wise co-normal derivative at point 0, because we are putting the control on the left part of the domain. Okay, the main theorem are the following. If we put the control on the second component, we will see that regardless the choices of the parameters alpha and A, alpha is non-negative and A is a real number, for any given initial data from the abstract space H-1, we will have the controllability. And the control cost is C exponential of C over T, where C is the constant that depends on gamma 1, gamma 2, as well as the parameters alpha and A. But as soon as we will put the control on the first component Y1, then the controllability things will depend sensitively on the choices of the parameters alpha and A. and this has been written over there. Well, for that case, we will fix gamma 1, gamma 2, the diffusion coefficient to be 1. And the reason is we need to perform in this case the spectral analysis approach. And for any arbitrary gamma 1, gamma 2, the things are quite complicated to understand. In this case, there will exist a set script R such that if we choose the parameters alpha A outside the set script R, then the null controllability will hold true for any given initial data y0 from h minus 1. But as soon as we will choose the pair alpha A from the set script R, then there will exist a subspace y alpha A of codimension 1 such that the controllability will hold true if and only if we choose the initial data from that subspace. In addition, the control cost and everything will hold true, but on the smaller subspace. Okay, so these are the main theorems in our case. So first I will start with the case when the control is acting on the second component. And as I told previously, that this case will be handled through a Kerlman approach. Okay, so before going to the main detail, I must say that if we start without any interior coupling, that is A equal to 0, as well as there is no boundary parameter, let's say alpha is 0, then the system 8 will be exactly equivalent to the scalar system or scalar problem 9 with discontinuous diffusion coefficient gamma x, that is gamma 1x in the interval 0, 1 and gamma 2 of 2 minus x in the interval 1, 2. They're also satisfying some kind of flux condition 10. And this kind of system has been already, in fact, the controllability of this kind of system with discontinuous diffusion coefficient has been by Abdullah in 2007. And we are taking their idea to take the Kerlman technique. So you can see that in the drawing of the interval, if I simply revert the portion 1, 2, the red portion as a mirror image through 1, then the system 9, 10 will be exactly equivalent to 2 equals to system 8 with A and alpha is 0. Now in our case, we will take the similar kind of idea to proceed with the Kerlman trick. Now, what are the Kerlman weight functions? This is the main important thing. Now, I must say that for the scalar system of the authors that I have just described in the previous slide, they have chosen a typical auxiliary function that I have drawn here for only one discontinuity point of the diffusion coefficients. In this case, you can see that the blue part has higher slope than the red one, and this is because we need the controllability or at point 0. I mean, we are putting the control at point 0, so the observability inequality we want at point 0, thus this has higher slope than the red part. And taking the idea from their paper, we will simply take the mirror image of the red part through the line of, at point 1. And this is the exact typical auxiliary function in our case, which are beta 1, beta 2, and I have the explicit expression also 2 plus ci times x minus 1, where c1 is simply 1 and c2 is some quantity that depends only on gamma 1, gamma 2, the diffusion coefficients, and it has large enough modulus, which is negative. Once we have this kind of auxiliary functions, then we will directly go to construct the weight functions, which are phi I and beta I in our case. I have written here, this is written in quite a standard fashion. I further introduce the space script Q, which consists of all the elements Q1, Q2 from C2, such that they're satisfying same boundary conditions as of the domain of A alpha. Now I write the theorem regarding Kerlman estimate. So this is the Kerlman estimate. It's quite standard. In the right-hand side, we have the observation integral that consists of the weight phi 2, eta 2, and the normal derivative of Q2 at point 0, because we put the control on the second component. So this is the good Kerlman estimate. We also have some source integral that has to be absorbed by some some integral in the left-hand side that I will discuss in the next slide. There is also some boundary integral in the Kerr-Lehmann estimate, that is SQ lambda q and integration phi1 eta 1 q1. This is in the observability inequality. Well, so from this Kerr-Lehmann estimate, I have written in this slide again. The first thing is to absorb the bad integrals in the right-hand side. So I recall the solution Q to the joint state satisfies the set of equation 11, and from that, the bad source integral will simply reduce to the integral 0 to t, 0 to 1, exponential minus 2s eta 1 and aq2 square. And this can be estimated by the integral x tilde that correspond with phi 2 exponential minus 2s eta 2 and q2 square. And this is happening because of the choices of the auxiliary functions beta 1, beta 2. Since beta 2 is bigger or equal to beta 1, that is exponential of 2s minus 2s eta 2, this will be larger than exponential of minus 2s eta 1 for any s greater than 0. And thus this term can be estimated by the term x tilde. And finally, for large s or large lambda, the integral x tilde can be dominated by the corresponding integral in the left-hand side. And this is the inequality, the final inequality, which is 12. And from here, after some standard computation, one can obtain the observability inequality, which is 13. The norm is Q0 H norm, and in the right-hand side, we have the good observation terms del x Q2 and the control cost exponential of C over T. Now the observability inequality is there, so by some duality argument HUM, we can prove the null controllability of the system when the control is acting on the second component. Well, so this is the first part, and then I will go to the case when the control is acting on Y1. So before going to the main detail, I will say something about why the Kerr-Lehmann trick is not working. So in this case, the term will be B1 star Qt, that is nothing but the co-normal derivative at point 0 of Q1. And to obtain the good Kerr-Lehmann estimate, we need the functions beta 1, beta 2, which is kind of the opposite of the previous one. In this case, we need beta 1 to have higher slope than beta 2. And for that, and in this case, we also have Kerr-Lehmann estimate with the observation integral given by 14. But the main thing is that the proper observability inequality is lacking. And this is due to the fact that the source term, which is exponential minus 2s eta 1 aq2 square, that cannot be absorbed by the corresponding term in the left-hand side. Because of our choices beta 1, beta 2, since beta 1 is bigger or equal to beta 2, so exponential minus 2s eta 1 is always larger than exponential minus 2s eta 2. So this kind of weight function is not enough to give us good observability inequality, and thus we will proceed this case by moments approach. In fact, we will see while dealing with the moments technique that the controllability will sensitively depend on the choices of the parameters alpha and a, which is not the case, which was not in the previous case. Okay, so I start with the spectrum analysis, which is the main ingredients to handle the moments technique. The set of equations 17 is the eigenvalue problem, A star alpha A u equal to lambda u. I will divide the spectrum analysis into three parts. First one is localization of the spectrum of this non-self-adjoint operator. And if I denote the spectrum of this non-self-adjoint operator by lambda alpha A, we have this lambda alpha A can be included in the infinite union of the disk that has center lambda and radius 2 times modulus A, where this lambda is the eigenvalue of the self-adjoint operator A alpha. Well, typically it is A alpha 0. And this can be proven quite simply. This is algebra. If we start with any xi from the resolvent set of A alpha, then one can show that A star alpha A minus xi is also invertible, and thus this Xi will also belong to the resolvent set of A star A alpha, alpha A, and that's it. So this is the localization of the spectrum. Then the set of eigenfunctions and eigenvalues. The first case is where lambda is equal to 0, and this is a very particular case, and it is possible if and only if A plus 3 alpha plus 6 equal to 0. And in this case, the eigenfunction is denoted by phi 0x. This will never give us any trouble that I have checked, at least in the approximate controllability case, and as well as for the non-controllability. The case when lambda not equal to 0, the set of eigenfunctions are denoted by phi lambda x. The first component has quite complicated expression, and this will lead some problem in the approximate controllability issues, and that I will show in the next slides. Okay, the set of eigenvalues were lambda. Mu is the square root of lambda, and the eigenvalues or mu are satisfying the equation 18, f of mean equal to 0. In the equation, we have some transcendental. This is a transcendental equation that has sinus. The parameter a and mu, they also appear here. Finally, completeness of the set of eigenfunctions can be drawn from a theorem of Keldy's, since our perturbation M A star is bounded. We have chosen a parameter which we're not letting it to go to infinity. Okay, then the description of the spectrum, the final part of the spectral analysis. For that, I first denote the set of eigenvalues of the self-adjoint operator A alpha by lambda k1 alpha and lambda k2 alpha, where lambda k1 alpha is approaching k plus half square pi square as k is going to k is large. And lambda k2 alpha is simply k plus 1 square pi square. And the lemma regarding the description of the spectrum is the following. There exists some natural number k alpha a, depending on alpha and a, such that for each k bigger equal to k alpha a, the operator, the non-self-adjoint operator A star alpha a, has two real eigenvalues that are denoted by lambda k1 alpha a and lambda k2 alpha a. In the disk D, with center lambda ki alpha, that is the eigenvalues of the self-adjoint operator with radius 2 times modulus A. And these two eigenvalues are satisfying some kind of asymptotic estimate for large k. Of course, two asymptotics, we can have that, we can tell that there exists a good spectral gap and everything. Well, finally, the uniqueness of the real eigenvalues in each disk, this can be proven using a perturbation argument by, it is there in the book by Kato, so we are taking the same idea to prove in our case, the uniqueness. Finally, the conclusion of the structure of capital lambda alpha, that is the set of eigenvalues. We deduced from our previous analysis that this can be written as union of two different sets, where the first one is lambda 0 alpha that consists of finite number of eigenvalues, possibly complex, so can be put in a finite union of disks, and lambda infinity alpha, which is nothing but all the real eigenvalues of the non-self-adjoint operator. And so this is the structure of the spectrum, typical structure of the spectrum. This has been drawn numerically in Scilab. You can see that I have plotted here for a equal to 30, the coupling coefficient, and alpha is 0.1. And the left part, we have some complex eigenvalues. They are in pair. And the right part, there are infinite number of real eigenvalues, which is coincide with our theoretical result. Okay, so then I will move to the approximate controllability issues. I write here the system again for better understanding. The control is acting on the first component. So for any given coupling coefficient which is non-zero and alpha non-negative, there exists a non-empty set skipped R such that we have the following properties. If we choose the parameters that does not belong to the set skipped R, the problem will be approximately controllable at any time in the whole space H minus 1. But as soon as if we choose the parameters from the set skipped R, then there exists a subspace Y alpha A of codimension 1 such that the approximate controllability will hold true if and only if we choose the initial data from that subspace. The proof is quite technical, but I will sketch the proof shortly. So it is stepwise. I start with the expression of observation observation terms, which is B1 star phi lambda. It is given in equation 20. And if I suppose first that B1 star phi lambda is 0, then it will give rise to one equation, that is 21. And also you will recall here the set of equation, the equation that's satisfied by the set of eigenvalues, which is 22. And we will finally write the set of equation 21, 22 as a system of equation, that is 23. By some technique, we can also prove that the determinant of the coefficient matrix is non-zero since we have A and mu non-zero. And thus one can write the solution sine 2 mu and sine square mu in terms of A, mu, and alpha. By some usual trigonometry, one can prove that the situation B1 star phi lambda equal to 0 can occur only if, that is necessarily when we have lambda is some critical eigenvalue lambda alpha AC, that is A times A plus 2 alpha plus 2 over R over 4, and this is some real eigenvalue. But we also need to prove that this is the sufficient condition. That is, we need to collect all the pairs alpha A such that satisfying the equation sine to mu and sine square mu to that expression. Okay, so I rewrite the equation in terms of 25A, 25B. That is, I put the value lambda alpha AC in the equation 24, that is appeared over there. So this is the set of equation 25A, 25B. So the solution curve of 25B will be necessarily a solution curve or a solution of 25A with negative sign. This is because of the trigonometry. So I have written here by the line that any solution of 25B that will necessarily satisfy 26 with epsilon equal to 1 and minus 1. So we have to collect all the pairs, all the solution curve of 25B there, which are satisfying 25A. In fact, the figure I have drawn it, the blue curves are the common curves of 25A and 25B. So we will collect all those curves on which the controllability, the approximate controllability will fail. And I denote the set by script R. There is a blue dot here, and this blue dot corresponds with the critical critical parameter. Alpha is 1 and A is some bad, big quantity, 3.19, 31469. So this is almost all about the approximate controllability. Finally, I briefly write things. To summarize, by Fattorini-Hotto's criteria, we have that if the parameters are not belonging to the set scriptor, then the approximate controllability will be in the whole space, as well as the parameters are falling into the set scriptor. We have one phi. For that, critical eigenvalue is 0. And thus, if we choose the space y alpha a, which is all those y0, such that it is satisfying the orthogonality, some kind of orthogonality conditions in a dual sense with the critical eigenfunction, then the approximate controllability will hold true only on this space if the parameters are from the set R. And the null controllability is just few lines. We have already proven the proper spectral gap property. We also have the record condition on the counting function that I didn't present here, but it is there in our paper. We also have proven a good observation estimate and the bound over eigenfunction. So the null controllability will be true depending on the choices of the parameters as of approximate controllability. So this is almost all for the theoretical part. So just we will perform some kind of numerics in our paper, but for the lack of time, I will not present here in detail. So simply I plot here, or I give the plot of the evolution in time of the control solution when the control is acting on the component y1. I have chosen the critical parameter. So we suppose, as theoretical the controllability should not hold true in the whole space, and this is there in the figure. We can see that at point t equal to 0.4, that is the final time, the y1 tx and y2 tx, they are no more 0. At least I think it can be seen from here. Well, we have used implicit Euler scheme in time, finite difference in space, and the penalized HM approach due to Gronsky, Lyons, and a very recent paper of Boyer. Okay, so this is the case when the control is acting on the first component. Now, when the control is acting on the second component, we say that controllability will hold true regardless the choices of the parameters. So even if we choose the critical parameters alpha c and AC, from the figure we can see, we can almost see that y1 tx and y2 tx are flat, they are 0. So we can say that, okay, this is matching with our theoretical result, and that's it for the second section. And then I will talk about some 3×3 model with one boundary control force, and this is mainly from my thesis. I have chosen here a 3×3 model, which is 29, appeared in the slide. I have an integral coupling of y1 to the equation of y3, which is ay1. And I also have the Kirchhoff type of condition, and depending on the situation, there are three different control problems when the control of the first, second, and third component respectively. Well, so this kind of problem can be also seen on a metric graph. In fact, this is a star-shaped graph with two edges. We have three components, but there are two edges because the first edge, we can think of considering a vectorial PD of y1, y3, because they're coupled to each other. And the edge of between n2 and 3 is nothing but a scalar equation of y2 only. So this is just a motivation to study some control problem where some of the edges can contain vectorial partial differential equation rather than only scalar one. Well, the contributed results are the following. If we control the first component, that is n1, then it will give us conditionally controllable depending on the choices of the parameters. And this is similar with our 2×2 result. If I control the second component, then it will be always controllable regardless the choices of the parameters. But as soon as we will put the control on the third component, it will never be even approximately controllable. I mean, not even approximately controllable in the whole space, because there are unobservable modes, as I have proven in the thesis. Okay, so this is almost all for my presentation today, and some further problems and results that I'm currently investigating is the following. What happens if we choose the coupling coefficient A to be L infinity in the interval 0, 1 in the 3×2 model? And some result that I have already obtained or obtaining, kind of. When the control is acting on the second component, a minimal time for null controllability is appearing, at least when the integral 0 to 1 ax dx is 0. Obviously, a is not equal to 0, Mr. Viewer. And here also, if we put the control on third component, it will not even approximately controllable. But if I put the control on the first component, it's quite complicated because we have already seen previously that controlling the first component will give rise to some unobservable modes depending on the parameters. So if I choose a function instead of a parameter, then the case will be really complicated to handle. And so for this, a careful investigation is really important. And this is almost all for today. And thank you very much for your attention. Thank you very much.
Okay, thank you very much for this interesting talk. And we have
I think the internet
some
connection
time
was
now
okay, right?
to... Sorry?
Okay, I asked that the internet
Sorry?
connection was okay?
Yes, yes.
From my
Well,
side, the
at
internet
least I have...
connection was okay.
Okay. Well, is there any question, any comment? We have time for 2 or 3 comments now.
Well, maybe. Do you hear me?
Yep.
Yes?
Yeah. You have shown quite a nice numerical results, and the computation is by this method, or how did you compute?
Okay, so this is by penalized HO method, and we computed via the finite difference scheme for the space and Euler scheme in time.
Mm-hmm.
Yes, in fact, we mainly took the idea from the paper of Frank Boer, where he has nicely presented the penalized HO approach.
Okay, I see.
From, yeah, so from taking the idea from his paper, we mainly plotted the figures in Scilab mainly.
I see. Thank you.
And, yeah, thank you.
Any other question? Okay, I have a question regarding the first part of your talk.
Okay.
In the first part, you have the non-scalar problem, the initially non-scalar problem, to a scalar problem with discontinuous coefficient. And then you have applied Kaleman estimates in order to get the controllability.
Yes.
Well, my question is if you have looked at any generalization of this technique to a problem in in a higher dimension, higher spatial dimension.
Okay, so at least for boundary controllability, I'm sure that the problem in the higher dimension space will be complicated, because in that case, even if we want to put the Kaleman estimate, there will be some kind of, how to say, the tangential derivative term will appear in the boundary integral, and that is not easy to absorb in terms of good terms in the left-hand side. So in higher dimensional cases, I think that things will be quite complicated to handle. I don't think so that Kaleman will give in the boundary controllability case. For the integral controllability,
Okay.
I think in higher dimension it could give a nice result, but not for the boundary controllability.
Okay, thank you.
If I may.
Any other question or comment?
Yeah,
It's
I have one. So Kuntal here, I just want, so first I would like to thank you for your talk. It was really nice. And I was wondering, in this case, where you have these two equations and where you can do everything with the Kaleman approach, it seems that what is important is that the coupling is lower order term, right? This is
Yes,
A of
yeah.
Y1. But here you took a local term, but maybe a non-local term. Say, for instance, if this is the integral of a Y1, would you be able to do something? I would suspect you can, because you have a strong difference in the size of the weights.
Yes.
So I wonder if you thought about that.
Okay. Yes. In fact, I didn't thought about that. Didn't think about that. Thank you very much. So you mean that if we put A times integral Y1, yeah.
Yes, for instance.
Yes, for instance. Yes, this can be done. Yes, you are right.
Well, I wonder.
We
You
can
think
also
it can be
use A
done?
times S.
Because I remember I have seen recently several works on non-local terms in space.
Okay.
So yes. I think there is one by Victor Hernandez Santamaria, right?
Yes.
And so I was wondering if, if here you could say something in that case. That's all.
The thing is that, of course, I didn't think about that, but it's a nice question. I can't think about this. Yes. Thank you.
Okay. Thank you.
Okay, thank you very much. So we are going to pass now to the second talk by Rogelio Ortigosa, who is there. Can you
So,
please
Yes. Yes, I
share
am.
your slides?
Okay. Can you see my screen now?
Yes.
Yes.
Yes. Okay.
It might take a few seconds or okay. Yes, everything okay?
Okay, everything's okay. So we are going to start with the second talk. The second talk, as I have said, is by Rogelio Ortigosa from Universidad Politécnica de Cartagena. And it is work in collaboration with a lot of people that you are seeing there. And the title is Optimal Control in Finite Elasticity and Optimal Design in Electromechanics. So, come on.
Okay. Thank you very much for the introduction. Let me ask you a question, please. Can you see my cursor over the screen?
yes.
Yes.
Yes? Okay.
Yes.
Then I'll go into... okay, how to get rid of this? Yeah, here you go. Presentation mode. So now can you still see my cursor?
Yes.
Moving
It's okay.
over the screen? Okay.
Yes, it's okay. It's okay.
Okay, thank you very much. Okay, thank you very much for the introduction. I have changed a bit the title of the presentation, which is incorrect. It should be Optimal Control in Finite Strain Elasticity and Optimal Design in Electromechanics. Okay. The reason why I have changed it is because I'm going to split my presentation into two parts. The first part is going to deal with optimal control, and then the second part is going to be related to optimal design in a multiphysics problem. So I will start with the first part of the presentation, which has to do with optimal control in finite strain elasticity. In finite strain elasticity, I always start with this slide. It is a slide where I have two configurations. On the left-hand side, you can see the undeformed or material configuration of a solid. And then, as a result of the exertion of a force or any action on the material configuration, we end up with a deformed configuration on the right-hand side, okay? So we have material or undeformed configuration, and then we have the deformed configuration on the right-hand side. And for every point capital X of the left-hand side of the undeformed configuration, we have a mapping which relates the material with the deformed configuration. And that mapping is denoted as phi, okay? We assume sufficient regularity conditions on phi. We assume that it is injective. And then associated with phi, with the mapping phi, we can define the material gradient, the deformation gradient tensor, which is what I call as F, which you can see here. So F is the material gradient of phi. And by material, I refer to this nabla zero. And this nabla zero is gradient with respect to capital X. So with respect to coordinates in the material configuration. Okay? Associated with F, we can define its determinant, which is denoted as the Jacobian, and then we can also compute the cofactor H. And these are the main kinematic entities that we are going to see in finite strain elasticity. Okay, now that we have covered the very basics of kinematics, I'll show the boundary value problem in finite strain elasticity. The boundary value problem is the one that is shown in the second box of the slide. So in the second box, I'm presenting the boundary value problem in the material configuration, denoted as omega 0. You can see the picture on the right-hand side, omega 0. That denotes the material configuration of my solid. And in that material configuration, I have a compatibility equation, which is automatically satisfied because F is defined as the gradient of phi, and hence its curl is going to be 0. That's the kinematic compatibility equation. And then the second equation is the equilibrium equation. There is a material divergence of a stress tensor P. P is the first Payola-Kirchhoff stress tensor, all right? And that is balanced with a volumetric force B0. And that needs to be solved, or that is valid for the entire domain omega 0, sorry. In addition to that, we have Dirichlet boundary conditions for the displacements or for the mapping phi, and also Neumann boundary conditions. And then we close our boundary value problem with a constitutive relationship, which is what appears in the last box. Basically, this is done through a strain energy function E, okay? And its derivative. Can you hear me? Because I got a message that my connection is unstable.
Yes. Well,
Yes, we hear
at
you.
least.
Yeah, it's
Yeah,
fine.
yeah.
Yeah, I
Okay,
hear.
thank you very much. Sorry, I panicked. Okay. So, and in addition to the boundary value problem, like as I was saying, we need a constitutive relation, and that is given in terms of a strain energy density E, whose derivative provides the relation between F and the first Pilot Kirchhoff stress tensor. Okay? What kind of constitutive relationships are we going to advocate for? Well, we will advocate for polyconvex strain energy densities. This is what appears in the next slide. This means that the strain energy density E needs to be written as a convex combination with respect to an extended set of arguments, F, H, and J. So the kinematic entities that I presented at the beginning, right? So examples of polyconvex energy functions. So one is the Neo-Hookean model. As you can see, the Neo-Hookean model, this NH, right? The Neo-Hookean model will be convex with respect to F and its Jacobian. Also the Mooney-Ribley model, the MR, which is convex with respect to F, H, and J, and the Ghent model. So examples of polyconvex models. So I've presented kinematics, the boundary value problem in finite strain elasticity, some notions about constitutive relationships, and I have introduced polyconvexity, and then I will present the weak form associated with the boundary value problem, which is nothing else than this that appears here. This is the weak form, and it can be seen, it is very simple to show that this is the Euler-Lagrange equation of this energy functional pi, or the stationary condition of the functional that I'm showing in this box. And in this box, you can see and you can identify the strain energy density W that I was referring to, and which needs to be polyconvex. And why does it need to be polyconvex, or why do we want to advocate for polyconvex strain energy density functions? Because then we can guarantee existence of minimizers to this functional pi, okay? So polyconvexity plus other growth conditions will ensure existence of minimizers to the functional pi that I'm showing in this box. Okay, this covers the very basics of finite strain elasticity. Now I will move to the control. And I will show a very particular type of control, which is a biomimetic type of control that we have explored in a recent publication of ours. And this is a control which is related, which is actually very similar to the actuation mechanism occurring in the fibers of our heart, okay? And this control is modeled, as you can see in this line. So it's modeled through an additive decomposition of the strain energy function. Our strain energy function is now going to be decomposed into a passive component, which could be a Mooney-Ribley part, this W of F. And then we need to have another component, another invariant, which depends on the deformation gradient tensor and on the control M. M is going to be my control. And specifically, that energy associated with the control will adopt the form that you see in there, this minus m/2 FA. What is F? What is A? A stands for fibers. We are going to consider fibers all over omega 0, all over our domain. And those fibers A are in the material configuration. So that when multiplied by F, I do a push forward into the spatial configuration. So this is a type of control that I'm considering. And of course, if I compute the derivative with respect to F, I get the first Payola, which is going to be additively decomposed into a passive and active component. It will have an active component. We need to bear in mind that we need to establish some upper bounds on the value of M if we don't want to compromise the polyconvexity of the overall energy, okay? So since our energy is now decomposed additively into two parts, our variational principle from which we need to compute minimizers is going to be the one on the box, where now the polyconvex energy function is decomposed into a passive and control components. Okay? So this is the type of control that I'm going to be considering. Now, what we are going to see now is what the control problem is. So typically in optimal control of solids, what we want is the following. We will start with a configuration and the form configuration omega 0 that you can see here. Then we will act on omega 0 through the control M, and this control will deform omega 0 such that it occupies a configuration omega. Okay, the form configuration omega. Configuration omega, which is in equilibrium. Okay, so that the mapping phi is a minimizer of the energy potential pi. And the objective is that omega, which has been actuated through the control, needs to be as close as possible to our target configuration omega d. Okay? Hence, our optimal control problem is formulated in terms of an objective function. And that objective function is going to measure somehow the distance between the domain omega and the target domain omega d. And how do we measure that distance? There are several possibilities, but recently in one of our papers, we explored the Hausdorff distance between domains. So basically the Hausdorff distance between the deformed configuration omega and the target configuration omega d. And the definition that you see in the box is the formal definition of the Hausdorff function, the Hausdorff distance. And as you can see, there is a maximum, a supremum, and an infimum involved, which means that this is not differentiable. Hence, what we did is to propose a regularization of the Hausdorff functional, which is the one that appears here. I'm not showing the regularized version of the Hausdorff functional because then I would need 2 slides just for the regularization. But then the key idea is that this regularization endows our Hausdorff distance with differentiability properties, and hence we can make use of gradient algorithms. All right? And in this gradient algorithm, as it is standard, I will include an objective function j, which will include, as you can see, the Hausdorff distance and possible regularization terms. You can identify the Tikhonov term there. And of course, we need to enforce the equilibrium equation. So basically that phi is a minimizer of the potential pi. And with this Lagrangian, what we need to get is a descent direction, basically the derivative of the Lagrangian with respect to my control, with respect to the control. And this is a standard. Basically, we would compute the optimality conditions, and then I would compute based on the optimality conditions, the descent direction, and that descent direction can be passed on to a gradient algorithm like F-min-con or whatever. Okay? And then some results associated with all this background. So in this example, what you can see is we started with a initially straight undeformed configuration, all right? And the objective was to reach the target configuration represented by this transparent surface, all right? Which has the shape of an S. And then what you can see is the evolution of the deformed configuration throughout the different optimization iterations. You can see as the optimization iterations progress, the deformed configuration start to perfectly match that of the target configuration. Okay? We tried this also in this different example in which we had a perfectly straight beam, the brown region, and then we had a target configuration represented by the transparent curved geometry. And you can see that as the optimization iterations progress, eventually my deformed configuration is going to perfectly match that of the desired configuration. And this is all I wanted to cover regarding our recent developments on optimal control in finite strain elasticity. I went very quick, but I think that I gave the main ingredients. Okay, now I'm going to talk about a different problem in a different context, in a multiphysics context, which is nonlinear electromechanics. And specifically, I will focus on dielectric elastomers. So dielectric elastomers are elastomers, which means that they can be stretched. They can deform a lot. They can deform even 500% their initial length. They can deform a lot. But on top of that, these materials have electromechanical properties, all right? So that when they are actuated electrically, they deform. For instance, you can see the figure here, where you have a dielectric elastomer, and then we place electrodes on top and on bottom. And then when we put a voltage gradient across the electrodes, the material tends to expand in plane and contract in the thickness direction. All right. This is a very simple experimental setting, and you can see what happens if you go for a more complex experimental setting, which is what you see below. This initial, I don't know, bubble, elastomeric film is non-active, and then when we activate it through an electric potential, you can see the magnitude of the displacements, of the electrically induced displacements. Because of these massively electrically induced displacements, these materials have been identified as very good candidates for soft robotics, and they are being explored currently in soft robotics. And as they are very good candidates in soft robotics, it is very important to control them and also design them properly. And we are going to focus on this part of the talk on the design of these materials, all right? But first I need to cover the governing equations, basically the boundary value problems, underlying the physics of these materials. And the PDEs associated with these materials are the ones that I'm showing here. The second one is exactly the same that I presented in the context of finite strain elasticity. Exactly the same. And the first one is very similar. In the first equation, you can see, in the first box, you can see the first equation, which is the Faraday law. The Faraday law is immediately satisfied through the introduction of a scalar field, phi. And that phi is called the electric potential. Okay? The second equation is the Gauss law, where you can see the material divergence of a vector field D0, and that D0 is called the electric displacement field that needs to be balanced with a volumetric charge ρ0. Okay? In addition, we need to impose Dirichlet boundary conditions on the electric potential phi. Okay, and we also could have Neumann boundary conditions. So we have a set of coupled PDEs, and those coupled nonlinear PDEs will be coupled through a constitutive relation given in terms of a strain energy density. A strain energy density which now depends on the deformation gradient tensor and on the electric magnitude D0. Okay. And what type of strain energy densities are we going to consider? Well, polyconvex strain energy densities. But now we are in a multiphysics context, which means that polyconvexity needs to be defined in this context, which means that the strain energy density E needs to be convex with respect to F, the cofactor, the Jacobian, and two more electromechanical fields, basically. D0, which is the electric displacement field, and another vector which is computed as F times D0. So an example of a polyconvex electrically enhanced electromechanical model is the one that you can see here. And as you can see, it is additively decomposed between a purely mechanical part, which is a Munich-Rivlin model, and then a second part which encapsulates the coupling, all right? So with this setting, I will not deepen more into the theory, but what I'm going to mention is that very recently we did topology optimization of dielectric elastomers, very recently in this paper that you can see here. So I will explain very briefly what this example is about. Very briefly, you can see that we have an active layer and a host layer. The host layer is not going to be optimized. We will only optimize the active layer, the brown layer, which is a dielectric elastomer. And you can see also the electrodes on top and bottom of the active layer. And what we did is to do topology optimization on the active layer so that we can optimize or maximize the vertical displacement of this point A. So basically, we optimize the actuation properties of the material. But what you can see here is a nice deformation, but this deformation is very simple. It's a simple bending characterized by a constant curvature. Okay, but now the challenge is what I'm going to present now. What happens if instead of these simple electrically actuated deformations, we want to get more complex shapes characterized by spatially varying curvatures? In that case, what do? In that case, we don't optimize the material. We don't optimize the active layer. In that case, we do something radically different, which is what I'm going to explain now. For that, we need to adopt a very radically different engineering principle or design principle. In this case, we need to adopt a layer by layer design layout, which means that we are going to consider layers of elastomer that you can see there, and intercalated, we will consider electrode regions. These denoted as E1, E2, E3 are electrodes region. And in those regions, I'm going to try to place my electrodes. There, I will try to place my electrodes, and I will try to optimize the shape of the electrode. It is now the electrode that I will try to optimize in order to get complex shapes as the ones that you see in the right-hand side. Okay? But optimizing the electrodes entails a complexity. What is the complexity? Well, the complexity is the following. I need to have a characteristic function which characterizes at every surface the presence of the electrode. For instance, look at the left-hand side here. The brown region represents the electrode. And this electrode, throughout the optimization problem, is going to evolve, is going to change. This means that either with this characteristic function, I do remeshing and I use a mesh that complies with the electrode regions, because those electrode regions are the regions where I will prescribe Dirichlet boundary conditions. Okay, so I will have moving Dirichlet boundary conditions. So either I do remeshing or I impose the Dirichlet boundary conditions weakly. So I don't want to do any of those. Instead, I'm going to do something different. I'm going to regularize the problem. How do I do that? Well, I will replace the characteristic function with a phase field function which is continuous. The characteristic function was discrete, was taking ones or zeros. Now I will play, or I will play with a function that adopts continuous values in the interval 0, 1. 0 means no electrode, 1 means electrode. Something in between means a blur interface. In addition to this continuous representation and diffuse of the electrodes in those surface layers, I will make use of a volumetric extension. So the presence of the electrodes is going to be taken into account in these intermediate regions, in the volume of the elastomer. How? By solving this Laplace problem with Dirichlet boundary conditions. And on top of that, I will make use of something very common and very standard in topology optimization, which is an energy interpolation scheme. With this, I'm not going to go into detail because I don't have time, but what I'm doing is I'm encapsulating and I'm taking into account the presence of electrodes within a point of the elastomer, so that what I can make the material active or inactive depending if I have electrodes on top and bottom or not. Maybe this was a bit confusing, but I can explain it better later. So this means that I replace my characteristic function type approach by an approach which is diffuse and where the material is active or inactive based on this phase field function within the volume. Okay? So now I'm in a position of explaining the optimal design problem. The optimal design problem is going to be very simple. Basically, I want to minimize an objective function, and that objective function could be the distance to a target configuration. And that needs to be subjected to some constraints. And the constraints are going to be the weak forms that represent these weak forms, basically equilibrium, mechanical and electrical equilibriums. On top of that, I will have a constitutive model, an energy interpolation scheme, a Laplacian extension into the volume, and I will have phase field functions which are restricted to the surfaces. Okay? Okay, associated with this optimal design problem, we can construct a Lagrangian, and that Lagrangian is the one that I have in this box. Okay, that Lagrangian includes the objective function J and the weak forms for the mechanical and electrical problems. And from that Lagrangian, I will compute the sensitivity, which is what appears in the second box. And with that sensitivity, I will be able to evolve the surface of the electrodes. So basically, I will be able to evolve the functions psi e. How? Well, making use of some principles in the field of phase transformations. This means that I will be able to evolve the functions psi e through this equation, which is typical from phase field transformations. You can see, for instance, the double well potential phi, which appears on this figure. Okay? Okay. And then I will show some results. For instance, in this example, what I have is different points on a disk, but I'm going to focus on points B, A, D, and C. And what I want is to minimize the vertical displacement or the Z displacement of point B and D and maximize the displacement of A and Z. And C, sorry. And for that, I started with an initial guess. This is my initial distribution of the phase field in all the 5 layers. I'm having 5 layers of electrodes. And as a result of my optimization problem, I end up with these optimized electrode configurations. You can see extruded vision of the elastomer. And you can see extruded vision where you can see the optimized electrodes. And this on the right-hand side is nothing else than the final deformed configuration. Alternatively, I can focus on a different type of actuation mode. And in this case, what I did is to maximize the vertical displacement of points A, B, C, and D, and minimize the vertical displacements of green points, basically. I started with the same initial guess, and then after the topology optimization process, I got the optimized topology of the electrodes on the 5 layers. You can see it in blue and red. And as a result of those electrodes, when I applied the voltage, I got this deformation, which is exactly the deformation that I wanted. And I don't know if I was too fast, but this is actually the end of my presentation.
Okay, thank you very much. Thank you very much for this very nice talk. And we have now a small time to comments or questions. Is there any question?
Oh, yes, if I may.
Yes, of course.
So here in your optimization problem, this is strongly nonlinear, right?
It is very nonlinear.
So how do you guarantee that? So you are doing computations with descent algorithm, I guess, right? Mm-hmm. And then how do you guarantee that? Well, in both problems, first problem? I guess, no?
Okay.
Well, maybe on the first problem. Let's go on the first problem. And so then how do you guarantee that what you have is the best and that you are not stuck in a local minimal or something like that?
You cannot. You cannot. The problem is non-convex.
Okay.
Even the energy is non-convex. So even you can have multiple, forget about the optimization. just focus on one example where you don't have optimization. So basically you have a fixed control. You could have buckling, which means that since your energy is not convex, you don't have uniqueness of solutions.
Yeah. And so is it something that you observe here in your example?
I haven't observed, no, because these examples are prepared to not to have buckling. If you want, if you are expecting to have buckling, you need to go to something very, very wide, basically.
Okay, well, thank you.
May I ask a question to the same problem?
Yeah.
Of course.
Okay. Yeah. By the way, very interesting talk. Thank you.
Thank you.
I was a little bit unattentive, and one moment it seems unattentive. The function, the control function m in your first problem, what is that physically?
Well, I said at the beginning, I said that this resembles the activation mechanism that we have in the human heart. All right.
Mm-hmm.
So this is very similar to what occurs actually in the human heart. There are two ways of modeling the coupling in the human heart. One is called active strain and active stress. This would be the active stress approach. So basically, this would be a tension. This control M would be a tension acting along the fibers. In the context of the the heart, this tension depends on the electric potential that is propagating through the myocardium, and it actually adopts exactly the same form as this one. Okay. So it is a traction occurring along the deformed fibers of our heart.
And how can you control that? You don't have it in your hands.
I know, yeah. That's why I moved to the other problem, which is more physically realistic.
Okay.
This one is, yeah.
Yeah, I understand. It's clear. But it was very interesting.
Thank you.
Okay, thank you very much again. And well, if there is no other question, we are going to close. We are going to finish. Next week we will have a conference by Nicholas Burke. Sorry?
That Nicola Burke. Mm-hmm.
Nicholas Burke, yeah. So we hope you will be here again, and thank you very much for participating. Thank you to the participants of today, and also to all of you.